In this problem, we're looking at IQs, and it tells us what the mean of the population is for IQ scores and what the standard deviation is. And we're told IQ scores are normally distributed. So if we look at samples of a certain size, if we just looked at means of samples of those size, in this case it's 49. So every different group of size 49 has different people in it, is going to have a different mean IQ score. But if we looked at how all those mean IQ scores are distributed, the central limit theorem tells us those means from those samples will follow a normal distribution. That distribution is going to have a mean that's the same as the population mean. It does not change based off of the sample size. And the standard deviation is what changes based off of the sample size. The standard deviation is the population standard deviation divided by the square root of the sample size. So if we have groups of size 49, it would be 18, that's the population standard deviation, divided by the square root of 49. So our samples of size 49, the means of those samples would have this standard deviation here, close to 2.6 if you round. So notice that's smaller than the population mean. Every time we increase the sample size, the standard deviation of the distribution is going to get smaller and smaller. Because when you have larger samples, there's less room for variability. There's less variation. If you have a big sample, the really weird large values, someone with a really high IQ is more likely to cancel out with someone with a low IQ in the sample, because you have more people in the sample, the high and lows will cancel out, and you're more likely to get a mean of your sample that's close to the actual population mean. And that's what we're getting at here with part B and C. In part B, we're looking at groups that are larger. If we looked at all groups of size, in this case 144, the mean of those groups would again follow a normal distribution. That normal distribution would have a mean of 105, the same as the population, but its standard deviation is even smaller because it's the population standard deviation divided by the square root of the sample size, dividing by square root of 144 here, and we get 1.5. In this problem, we have a light that's flashing, and the time between its flashes has a mean time and a standard deviation, and we're told it's normally distributed. So typically, in this case, since the mean is 2.5, the light tends to flash every 2.5 seconds. It's not perfectly every 2.5 seconds. There is some deviation there, but that's how the light's set up to go. So in part A, we're finding the probability that an individual time is greater than 3.5. That would mean the light didn't flash. There was a period of 3.5 seconds before or in between the flashes. And so use our spreadsheet for work 3. We have a normal distribution with a mean of 2.5 and a standard deviation of 0.7. And so we're trying to see the probability that an individual time is greater than 3.5. So greater than 3.5, we would type that in here in the green. And it tells us that the chances an individual flash, the time between it is 3.5 or more, this right tail of the distribution. It gives us the probability of that. So then in part B, we're looking at the mean of 70 randomly selected times. So a sample here. And from the central limit theorem, we know if we look at samples of a certain size, so if we looked at samples, and they're all the same size here, in this case 70, if we looked at the means of those samples, it follows a normal distribution. And so all those means, they're going to cluster around the population mean. And in fact, that is the mean of the distribution. It stays the same at 2.5. But as the sample size gets larger and larger, which we discussed earlier in this video, the standard deviation gets smaller and smaller. They tend to cluster closer and closer to that population mean because there's less variability in the larger samples. So we need to figure out what that standard deviation is for groups of size 70. This worksheet again does it again. We look at our population standard deviation divide by the square root of the sample size, and we get, in this case, 0.083666. So you would type that in, and now we're looking at the distribution of means out of groups of size 70, and it has this mean and the standard deviation. So we're asking that same question. The probability that a sample of size 70 has an average of 3.5 is 0%. And that's accurate to, looks like 6 decimals there. And so that's our answer. Well, we conclude, if we're just selecting one random measurement, there is a probability, a chance that we're going to have that one measurement have a time in between flash of more than 3.5. But if we look at a group of size 70, the average of that group is not going to be more than 3.5. In fact, it's a 0% chance accurate to 4 decimals here. And so which one of those answers is more important, more significant? It all depends on the situation. In this case, the average of a group isn't that important. What we are more caring about is that individual flashes are happening on a regular basis, and then there's never a time when there's a longer pause in between individual flashes, because we need that safety light to flash to serve its purpose. And so it's more important that the individual flashes don't have a long pause in between them. And so part A would be more important.